-2s. We're going to do the second here polynomial assignment. I think it's assignment number 4 in total here. So this one's all about regression or analyzing a graph that they've given you already. So let's look at this and determine, based on the data they have here, which is the best type of polynomial regression that we can use. So remember, you can use the diagnostics in TI-81, or you can use Desmos here. So I have Desmos. I'm going to just punch the data into my calculator here. So remember, in the first column, you put all the x values. So I got, oops, that should be a 0. My bad. 1, 2, 3. Okay. Got all these extra lines here. Okay. Then in my y values, I'm going to put in all my second column. Or in the second column, put all your y values. Just say 1, 3, 7. Okay, so if you pulled up my sheet that we had before, this polynomial regression Desmos sheet has all kind of set up for us here. We're just going to look at all the r squared values to try to determine which is the best. You can see in the r squared values for linear is 0.69, for quadratic 0.89, and for the cubic one, you got a 1. 1 is the best, so that's the one we're going to use. I'm just going to zoom this here a little bit. Yeah, you can kind of see if I didn't have these on here, like that one, it goes through 1 point. Not very good. Oop. Pain in the butt, because this thing doesn't really turn that one off. And rats. Okay. And if that one, quadratic one, it has to do 1 point as well, but you can see the cubic goes through all 3 pretty nicely. Okay. I can do that. So cubic one's the best one here. So let's go back here, justify your answer. I don't have to justify my answer. It just has the best r squared value. So cubic, best r squared value. Equals 1. Okay. Write the regression equation. So the regression equation you could see here, they tell you what the A, B, C, Ds are here. So 3, 6, -1, and 5. So you just put that back into the equation. Oh, now I forgot now. Okay, so I'm just going to write that in here. So we have 3, so this is A cubed, 3x cubed. Then it has bx squared, so b is 6 squared, okay. And then it has plus cx, but the c is a -1, so I'm going to put a -1. Oops, no, don't put the c there, you're replacing everything. X, and then my d is plus 5. So there's my equation, okay. Next part of this says use the graph, determine the coordinates of any maximum or min points, stating that these are relevant or absolutes. I'm not too worried about the relative or absolute parts. Let's just get rid of that part. Okay. Relevant means, is it just that part of the graph, or is it absolute? Does it go on forever? So to find out the min or max points here, you just, if it's on Desmos, you just click the graph. Make sure you click the right point. These ones are pretty close. You don't want the y-intercept. You want the min-max points here. So there's my min and max points. So it says to the nearest hundredth here. So the max point that I have here is -1.421, sorry, the 9.93. Then I have a min value of, let me just move this out sideways here. These are both, well, I can get rid of this term here. Okay, these are both relative mins. Now the absolute maximum point, like if you look at the graph, it goes on forever upwards. So that's an absolute max. It goes forever that way, right? So that's the absolute. The relative one is just this, just the relative between those two sides. Okay. Should have vetted that question just a little bit better. Each year, a basketball team sells boxes of chocolates as a fundraiser to lower the cost of team fees. So we're going to try to analyze which regression is the best. We're going to use the equation, or I might as well just use the graph. To the nearest whole number that the team will have to sell to charge, if they charge $4.35 for a box. In 1 year, team only sold a certain amount of boxes. What price did they charge? That's not on here. Oh man, they didn't sell that many at all. They only sold 125 boxes compared to like the 5,000 or 3,000, 1,000 boxes here. I'm going to assume 125 and they're going to have to charge quite a bit. If the team raises the price too high, they will not sell any boxes. Use a regression to predict the price of a box that will result in 0 boxes sold, which actually might be this 125 number. So I'm going to go here. I'm going to go into my X and Y's here. Now, if you're in this one here, you just hit the backspace a bunch of times. You can see it just gets rid of the data. And then you don't want to get rid of all that stuff. So I've got 3, 4, 5.5, 6.5, and 8. Okay, let's go to that. And then you're going to go over to the Y values and put in the Y values. You can see it doing something over there. That's nice. Always nice to see things happening. Cool. I don't know if that should be a 0 on the other one there, but let's see what this looks like here. The reason you don't see anything is because the Y values are so large. So what we can do here is we can just keep on scrolling this until we see, so there's some data over there. Oh, we can see it goes up and then down. So again, we're looking at which one produces the best R value again. R cubed. The R squared of the cubed is 1 again. So the best one here is going to be cubic again. Yeah. And then we want to find the equation. So the equation of this is what I want to make big screen. I'll make this one smaller. So my equation, so ax cubed, so that is, oh, I want to raise this to the nearest hundredth, so negative 33.32x cubed. Okay. And then I want to go plus bx squared, so my b here is 771.31x squared. Okay, this is a really ugly equation. Plus cx, my c is a negative number, plus d. So just looking down here at the very bottom here, right? Because that's the r squared is cubed, or 1 there, so the cube is the best one. So I'm just using all those a, b, c, d's there for this equation. There you go, looking pretty good. Use the equation to find out if they sell the boxes, how many boxes would they sell if they want to charge $4.35. Okay, so if I go through the thing, I can trace through this and I can find the 435 right there, 435. So it looks, I look at the numbers there, so 2,866. It says use the equation, but I'm not too concerned about that. You could put in your x values if you want to. You could put all this into all your different x values. Hey, oh. All right, so you can put all these numbers into your x values here into the equation up there if you want to, or you can just trace the graph. You hit into TI, just hit trace and type in 4.35. And this one here, you're gonna have to just click and drag until you find the right value. And again, I forgot what the number was now. Right there. So 2,866. So 2,866 boxes. Okay, 1 year they only sold 125 boxes. So if they only sold 125 boxes, that's going to be somewhere down in this area down here. So because remember the y value is your box number. So what I'm going to do is I'm going to just go down here. I'm going to type in y is equal to 125. You can see that that creates a line going across here that intersects. And that point there says the y value is 125, right? And then tells me what the x value is. And that's how much you're going to have to charge. The x is how much they charge here. So $10.25 is what they had to charge here. $10.25. So if you're on your TI calculator, you'd make y2 is equal to 125. y1 being the equation, just find where they intersect each other. Okay. So where would this be 0? So I'm just going to get rid of this line that I drew here. It's right there. So I would sell 0 boxes if I've charged them $10.40. $10.40. Result in 0 boxes sold. There you go. So just using the regression equation. If I were to sketch that out there, it's right here is what we're looking for. Right? Where does it cross the x-axis? $0 sold. Or 0 boxes sold. Okay, so this one here, we're just going to use the graph to help us find stuff, find out like appropriate domain and ranges. What else do we have to do here? Yeah, explain why negative x-intercepts. So I'm just going to graph this out. So let me just go pull up Desmos here. I'm just not going to deal with this one right now. So I'm going to go find a new blank slide here. So I'm not doing a regression. I'm just going to type it in. Okay, so we can't use t's. So we're going to use x's to do all this. And 1.36. Okay, so here's my graph. You can zoom again, hold down the shift, kind of stretch it out, make it look better. You can pan, you can pick up the graph at any point, just pick it up and move it around. So this is what my graph looks like here. Okay, so first question says, what's the max point? Find the max height. So if my y-axis is my height and t is my time, because that's what it is, this is like saying this is my y and this is my x. So I'm just looking for the y values here. So oh, do I have to do the nearest what? I should go back to that question. Nearest hundredth, 8.89. 8.89. Now these probably have units. This is height is in meters, so this is going to be in meters, okay? Determine the height of the ball to the nearest hundredth at 2.5 seconds. I can go back to my graph. You hit trace 2.5, or just drag your cursor over until you find it. Right, was there for 2 seconds there. Right there, 0.86. 0.86. You can also just put that into the equation. You can just, if t is equal to 2.5 seconds, I could put that into this equation where all those t's are out there if I wanted to. If I just use the graph. Why not use the graph? Yeah, but why not use it? Okay. Determine when the ball is at a height of 8 meters. Okay, so this is going to be a bit trickier, so I'm just going to put 8 here. You notice that when I draw, oops, sorry, I go y is equal to 8, my bad. Y. Oh, I have my caps locks on, sorry. So y is equal to 8. You notice that there's going to be 2 times because it goes up and then comes back down. So there's 0.81, so 0.81 seconds. And because it comes back down, because it goes past that, because the height is 8.89, it comes back down, so it comes to 1.65. 1.65 seconds. State the y-intercept of the graph. So remember, you can just go onto the graph here. You just click the red graph. Oh, there's a dot there. I'll use that. The y-intercept is 1.36. Kind of knew that from the equation too, because it's in standard form. That's my constant value here. It's 1.36 meters. In context of the question, this would be the initial height at time is equal to 0. So just before it throws the ball, that's how high it is off the ground. Find the coordinates of both the x-intercepts here. So x-intercepts here, my graph's already selected. I can click on those two there. So you have this negative 0.11. I'll put that in here right now. Well, I want the coordinates. So negative 0.110. And what was the other one? 2.57. 2.57, and they want the other value too. So my y values, you notice that are 0. Y is equal to 0. Okay. State that the positive answer. State what the positive answer represents. The positive answer represents this one. That's the positive answer. It represents the time, because remember your x is your time. The ball hits the ground. Because h, this is my height, right? My height is 0. So h is, y is equal to 0. H is equal to 0. Right? Height is equal to 0. Now, why does the negative one, why is this not a valid answer? Because this means it has negative time. Time is never negative. Unless you're looking back in time, it just doesn't make sense that the ball would be on the ground in the previous history. I guess you could have picked it up and then threw it. It'd be kind of weird. Time is not negative in these kind of questions. It just doesn't make any sense. There you go. That's the end of that. Okay, I'll see you in the next video. Bye.